So welcome back. Hopefully you've had a little bit of a chance to crank out this example. Now I wasn't going to do all the details. I was just going to jump to the final part here. So if lambda is equal to 1, I can tell you what the eigenspace is. So the eigenspace, in this case, you should have found something that looked like this. All multiples of the vector 0, 1, 1 as t runs through the real numbers. Another way to think about this is it's the span of the vector 0, 1, 1. So this tells me the basis of this eigenspace. And similarly, we're going to look for the eigenspace of -1. And if you did that correctly, you should have found, make my parentheses a little bigger here, you should have found all multiples of the vector 0, 1/3, or 1. 0, 1/3, and 1 as t runs through R. So another way to write that is the span of the vector 0, 1/3, 1. Okay, so now just to kind of quick recap, because you may have forgotten over the break what we're trying to do here, is we have, whoa, so this example has been quite long. We have this matrix and we're trying to diagonalize. So we need to find the eigenvalues, which we did. It's 2, 1, -1. And then for each eigenvalue, we want to find the basis for the eigenspace. So for each eigenvalue, we found the corresponding basis for the eigenspace. And now we actually have enough information to construct the diagonalization. So you construct D from all the eigenvalues. You take D and you put your eigenvalues down the diagonal. Now it doesn't matter which order you do this step. You can put the, I could have had 1, 2, -1, I could have had -1, 1, 2. That part doesn't matter. But once you pick the order here, that's going to force the way that you're going to do the P. So the P is you're going to use the basis elements. And in the first column, what you want to do is you want to put the basis for the eigenspace of 2. So we would have 1, 1, 1. Actually, you can still see it on the corner of the page right here, over here. This is the basis for the eigenspace of 2. What about the eigenspace of 1? Let me scroll that back up. It's 0, 1, 1. So in the column corresponding to the eigenvalue 1, we put the basis of its eigenspace, and then for -1, we put the basis of its eigenspace. So that's my matrix P. Right, so let me make this a little clear. Keep same order as eigenvalues. Okay, so each eigenvalue has a basis, and you put that basis in the corresponding column. So if I had put the 2 here, this column would move over, and if the 1 was there, then that column would move in the same direction. And then that's actually it, because what we have is, and you can check, I'm not going to check all the details here, but you can check then that AP is the same thing as PD. Okay, and if you're a little bored at home, you can check that this is actually that's actually true. And this is similarly, this is the same as saying that A is equal to P times D times P inverse. Right, so this is the diagonalization. This is the diagonalization. Okay. So this is what we do in a special case, right? So just to remind you that what we did is we're using the fact that if we have n distinct eigenvalues, then A is diagonalizable. And this procedure will work for any matrix with n distinct eigenvalues. So if I had a 10 by 10 matrix with 10 distinct eigenvalues, you could just crank through this procedure and find the diagonalization. But then it leads to the question, suppose that A has less than n distinct eigenvalues. Can it still be diagonalized? What are we going to do? Okay, and the answer actually it depends. Okay, it depends. So there's some missing information here to decide whether you can diagonalize or not. So the details are in the next lecture. So hopefully you come back and listen to the sequel where we talk about diagonalization part 2. But the key ideas from today's lecture are the notions of similarity, diagonalization, and a procedure to find diagonalization with n distinct eigenvalues. So I look forward to I look forward to you watching me in the next lecture. Okay, have a great day.